Okay, good afternoon, everyone, or good morning, or good night, depending on what time of the day you're watching this. I'm recording this lecture in the Lightboard room in Jordan Hall. It's a new technology that the College of Science is investing in. And although I'm looking at the blackboard and writing on it, so if you're behind me, you should not be able to see what I'm writing because I'm blocking your view. Actually, the camera is facing me from behind the board, and it's being processed as it's being filmed and flipped around, so that you don't have to read mirror writing to read the lecture. Okay, so hopefully this will work out. Last time we had proved Turan's theorem, and remember that Turan's theorem concerns what is the largest number of edges that you can put into a graph on n vertices and avoid having a complete graph on r vertices sitting inside that graph. And we proved that this is exactly tr minus 1 of n, the number of edges in the Turan graph on n vertices with r minus 1 classes. You take the n vertices, break them up into r minus 1 blocks of as equal size as possible, and put all possible edges between the blocks and no edges inside any block. This graph obviously doesn't have a complete graph on r vertices inside in it, but we proved that it's actually the largest graph in terms of number of edges, which has that property. Now, we had given an estimate on how big this number of edges in this graph. The estimate was that it's at most n squared over 2 times 1 minus 1 over r minus 1. And we can also put pretty easily a lower bound on the number of edges. Well, we'll start with, we won't start with an exact. I will start with a lower bound. Each of the blocks has size at least the floor of n over r minus 1. And for each pair of blocks, therefore, I'm going to be getting this number squared, number of edges. And how many pairs of blocks do I have? I have r minus 1 choose 2 of them. And I'm not going to do the exact calculation here, but for sufficiently large n, the floor of n divided by r minus 1 is basically n divided by r minus 1. So what I'm basically getting here is n squared over r minus 1 squared times r minus 1 times r minus 2 over 2. And so I have my n squared over 2. One of my r minus 1s cancels with this guy, and the other one gives me the 1 minus 1 over r minus 1. So I get that the upper bound of n squared over 2 times 1 minus 1 over r minus 1 really is the truth. The precise statement is that if I look at the limit as n goes to infinity of, well, I want to write here the number of edges in the Turan graph, but we have Turan's theorem, so we already know that this is the extremal number for excluding kr. The limit of this quantity as n goes to infinity, if I divide it by n choose 2, which is the largest number of edges there could possibly be in a graph on n vertices, then that limit is equal to 1 minus 1 over r minus 1. So, of course, the upper bound in the implied upper bound in the statement comes immediately from this upper bound here. And we just have to do a little bit of fiddling with some epsilons to deal with passing from the floor function to removing the floor function. So that deals with the extremal question for complete graphs. But, of course, it begs the much more general question. Fix an arbitrary graph f. What is the limit as n goes to infinity of exnf divided by n choose 2? So in other words, for an arbitrary graph f, at most how many edges can I pack into n vertices and still avoid having a copy of f? And we're not going to get an exact answer like we had for Turan's theorem for general f, but it's reasonable to hope that we could get this limiting quantity. What is the greatest proportion of the possible edges that one can pack into a graph on n vertices and still avoid seeing a copy of f. So it turns out we can, for all graphs f, give an answer to this question. And the answer is going to turn out to depend on a certain parameter associated with the graph f that's of extreme interest in its own right. So probably what I will spend most of this lecture doing is talking about that parameter, which is called the chromatic number of the graph f. So here's our definition. For any graph G, the chromatic number, which we're going to denote by the Greek letter chi of G, it's going to be the minimum, let's say, OR, such that we can partition the vertices of the graph into OR blocks, A1 up to AR, with all edges going between different blocks. Okay, so the term I'm defining is chromatic number, which suggests coloring. So what has this definition got to do with coloring? Well, here's what we're to think of. We have our, okay, let's do an example. We have a graph. Let's say it's this graph here on 5 vertices. And what we're trying to do is we're trying to partition the vertex set into blocks, as few blocks as possible, so that all of the edges run between the blocks and we have no edge inside any block. Well, if we associate a color to each block, then basically what we're doing is we're assigning a color to each vertex of the graph with the property that no two adjacent vertices get assigned the same color. So what about this graph here? We could assign, let's say we have to assign a color to each vertex. Let's say we assign color pink to this vertex. Well, now, this guy here is adjacent to a pink vertex, so it certainly can't get pink, so it has to get a new color, let's say blue. What about this guy here? It's adjacent to a pink and it's adjacent to a blue, so it has to get a new color, let's say yellow. So we're forced to use at least 3 colors, at least 3 blocks, just to separate the vertices of this triangle. But what about these two guys? Well, neither of these two guys can be pink, but there's no harm in them being either blue or green. For example, they can both be blue. And we haven't violated the rule that the two edges must go between vertices in different blocks. So here we have one block of size 3, the blue block, one block of size 1, the pink block, and another block of size 1, the yellow block. This picture shows that if this is my graph G, then this picture illustrates that the chromatic number of this graph is at most 3, because I have exhibited a specific partition into 3 blocks. Can I do better? I don't think so, because I need at least 3 blocks to deal with the vertices of this triangle. So in fact, I can pretty quickly argue that for this particular graph, the chromatic number is equal to 3. So I've defined the chromatic number in terms of partitioning the vertices into blocks. But really, every time I talk about the chromatic number, I'm going to be thinking in terms of coloring the graph, coloring the vertices in such a way that no two adjacent vertices get the same color. So let me give myself some space, because I want to draw some pictures now. This guy isn't easy to erase. There we go. So the chromatic number of a graph first came up in a famous recreational problem, the map coloring problem. So back in the 1850s, English mathematician Francis Guthrie was, one rainy Sunday afternoon, he was playing with a map of the counties of England. And he noticed that he could color the map of the counties of England in such a way that no two counties that shared a boundary ended up getting the same color. And he could do that using only 4 colors. And he looked at other maps, and he noticed that no matter what map it was that he played with, he could always get away with coloring the regions using only 4 colors in such a way that no two adjacent regions ended up getting the same color. And he made the now very famous 4-color conjecture. So the 4-color conjecture was that every map can be colored with 4 colors with adjacent regions getting different colors. Okay, so this pen is useless. It has to be confined to the just to coloring in vertices. And let me move back to my green, which was working really nicely. So for example, suppose we have this country here, or this map here that has a country in the center, and then maybe there are these 5 countries scattered around the exterior of the map. Well, let's say I'm trying to color this map. Maybe I assign color green to this guy here. Well, now I'm going to have to assign a different color to this guy here. Maybe I'll assign it color pink. And what about this guy here? It's adjacent to something green and pink, so I'm going to have to give it a different color still, which is blue. What about this guy here? It's adjacent to a blue and a green, so I'm going to have to give it a different color. Now, if I give it a 4th different color, well, then I'll have already used 4 colors. So let me try to be as economical as possible, and let me color this guy pink. Now, this guy is adjacent to a pink and a blue, so I have to give it a color different from pink and blue. It could be a completely new color, but if I'm trying to be economical, maybe I will use one of the old colors, green. And now look at the last region. It's adjacent to a pink, it's adjacent to a blue, and it's adjacent to a green. So if I want to get away with not having adjacent regions colored with the same color, then I'm going to have to introduce a 4th color here. It may not be entirely clear, but this is green here, this is green, this is yellow. Oh well. Yellow, green, green, and then it's obvious that these 3 guys are different colors, or at least I hope it is. Okay, so this picture shows that you always need at least 4 colors. There are examples where 4 colors are necessary, and what Guthrie observed was he couldn't come up with an example where 5 colors were needed, and he proposed this problem to his math professor, August Morgan, and the problem has a very long history from that point that goes through various proofs and disproofs, and finally it was resolved in the late 1970s in a highly controversial proof that used heavy computer assistance. By now this is accepted as not a conjecture but a theorem, but it's a conjecture and theorem with a very long and interesting history. And in the class notes I mentioned some references if you're interested in learning more about this problem. So what has this got to do with graph coloring? I'm talking here about coloring a map rather than coloring a graph. But of course, you can easily translate a map coloring problem into a graph coloring problem by just taking each region of the map to be a vertex of your graph. So this would be a graph which has 6 vertices, 1 for each of the regions, and then you join 2 regions if they happen to be adjacent. So we have a ring of adjacent regions around the outside, and we have a region in the center which is adjacent to everybody on the outside. So the problem of coloring this map with adjacent regions getting different colors is the same as the problem of coloring this graph with adjacent vertices getting different colors. So the chromatic number is exactly the parameter of the associated graph that solves the original map problem. What's the least number of colors you need to color the map? I didn't choose this example completely arbitrarily. You might want to take out a map of the states of the United States and see how many colors you need to color the states so that no 2 adjacent states receive the same color. And not particularly surprisingly, you need 4 colors. And one of the reasons you need 4 colors is that you can find 6 states that are arranged in exactly this configuration. So there's a challenge problem. Without looking at the map of the United States, find the 6 states that look like that. It's pretty easy once you have the map in front of you. So the chromatic number came up in a very recreational way in terms of this map coloring problem. But it turns out that it is a parameter of graphs that is incredibly useful. It has applications in scheduling problems, in assignment problems, in allocation problems. It's one of the most important parameters associated with a graph. Let me give you just some maybe fairly silly examples. One example might be, suppose the vertices of this graph represent radio towers. And the radio towers are broadcasting at certain frequencies. And you have an edge between 2 towers if they're so close to each other that if they happen to be broadcasting at the same frequency, then they would interfere with each other. So then, what is a coloring of the graph? A coloring of the graph is an assignment of frequencies to the radio towers so that when all the towers are broadcasting at their assigned frequency, you have no interference. And the chromatic number is the most efficient assignment. It's the assignment that uses the least number of different frequencies. Another example, maybe the vertices of this graph represent 5 committees. And there's an edge between 2 committees if the 2 committees have a member, at least one member in common. Well, then what would a coloring of the graph be? Well, it would be, for example, an assignment of time slots in which the committees meet that satisfies that there is no committee member who is being forced to be in 2 places at one time. So this committee and this committee are not allowed to meet at the same time slot because they have a member in common. And then the chromatic number is the most efficient way of assigning time slots to the committees. It's the way that uses the least possible number of time slots. I'm reading a book about circuses at the moment, so here's an example inspired by that. These vertices could represent circus animals, and the circus is moving on to another town, so the animals have to be put into cages to be transported. But of course, you can't put any random pair of animals together into a cage, or maybe they'll eat each other, or one will eat the other. So you put an edge between 2 animals if, whenever those 2 animals are in a cage together, one of them is going to eat the other. And then a coloring of the graph is going to be an assignment of animals to cages in such a way that, a harmonious assignment, in such a way that the animals that go into a particular cage, none of them will eat each other. And then the chromatic number is the least number of cages you need to properly assign all of the animals subject to that quite reasonable and quite humane restriction. So, so this is an incredibly useful parameter of graphs, and it's one that's been studied extensively since it was first introduced in the mid-1800s. Given how useful it is, it would be nice to think that it's a number that you could pretty easily calculate. And it doesn't seem like it should be tremendously difficult. We certainly didn't have any difficulty in the 2 examples we looked at, but of course they're small examples. Unfortunately, it turns out that this is not a parameter that is particularly easy to calculate, or at least we don't believe that it is. We strongly believe that it isn't. So suppose I was to ask you the question, is the chromatic number of some graph G that I give you, is it equal to 2? Well, the answer is either it is or it isn't. And the good news is, as we might see later in the semester, this is very easy to determine. Very easy means that you can run an algorithm that, given any input graph G, will return the correct answer to the question, can you partition the graph into 2 blocks so that all of the edges run between the blocks? In other words, the graph is bipartite. It will correctly return the answer to that question, either yes or no. And it will run quickly. It will run in a time that's more or less linear in the number of vertices, maybe quadratic in the number of vertices. But certainly, it will run in a time that grows polynomially as the size of the graph grows. Unfortunately, if you replace the 2 with anything bigger than 2, for example, if you ask the question, OK, I'm going to give you a graph, and I want you to tell me, does that graph have chromatic number 3 or not? Can you answer that for me? Well, of course you can, because the graph has finitely many vertices. There are only finitely many ways to partition the vertex set into 3 blocks. And you can just check each of those partitions and see, does any of them work? If one of them works, yes, you have chromatic number at most 3, and then you can check, is it actually 2? If none of them work, then you know that the chromatic number is bigger than 3. But that, of course, is a ridiculous algorithm because it runs in exponential time in the number of vertices of the graph. So it could, for a very large graph, it could take an extraordinarily long time to complete that algorithm. But presumably, I mean, we're smart. Humans are smart. We develop tools. We develop mathematical tools. Presumably, we can develop some good tools that will solve a problem like this. Can you color the graph with 3 colors or not? Unfortunately, we haven't yet been able to determine the answer to this question. Not easy to determine. I say we haven't yet been able to. It's actually an open question. It's one of the most central open questions in theoretical computer science. It's the famous P versus NP question, if you know about that. This question, is the chromatic number of a graph equal to 3? This is a prototypical example of something called an NP complete question. And the P versus NP problem is basically asking, is there a polynomial time algorithm that solves this problem, or is there not? And if you could solve that question, you'd be a lucky man or a lucky woman, because the Clay Institute would actually give you $1 million for solving the question. At the beginning of the century, the Clay Institute created a collection of what they called the Millennium Problems, 7 problems which they considered to be central to 21st century mathematics. And they put a price tag of $1 million on each of the problems. We're 15 years into the century, and one of the 7 problems has already been solved. Perelman solved the Poincare conjecture and didn't take his $1 million prize, surprisingly. One of the 7 problems is this P versus NP problem. So at the moment, the best algorithm runs in time approximately 1.33 to the power number of vertices in the graph. So if the number of vertices in the graph is relatively small, that's quite all right. 1.33 to the power of 100 is not such a big number. But if the number of vertices is large, if it's 10,000, then an algorithm that runs in time 1.33 to the power 10,000, that runs in that many steps, is not really a practical algorithm given the expected lifetime of the universe. So the chromatic number is an important parameter. By just checking the time to see how I'm doing. The chromatic number is an important parameter, but unfortunately it's not a particularly easy parameter to get hold of. Before getting back to the Turan problem and to the problem of how many edges can you pack into a graph, avoiding the appearance of a certain subgraph, I want to maybe say a little bit about why it should be that this problem of computing the chromatic number, why it should be so difficult. So one way to get an idea of why it should be so difficult is to observe that although the definition of the chromatic number only talks about the graph locally, it only talks about pairs of vertices that are joined by an edge. So you can sort of check the condition just by making a small number of local checks, once for each edge of the graph. It turns out that the chromatic number really is a global property of the graph. You cannot deduce what the chromatic number is purely from local considerations. So I want to tell you about one result along those lines that I think is a very interesting and a very clever construction. And in order to get started on that, I want to introduce another parameter of a graph, which is the clique number. So a clique in a graph is, well, it's like a clique in everywhere else. It's a collection of buddies. It's a collection of vertices that are mutually adjacent. In other words, it's a copy of the complete graph on all vertices sitting inside in a graph. The clique number is the largest clique that's sitting inside in a graph. So omega g is the maximum OR such that KR is a subgraph of G. So for example, this graph that we had before, the clique number of this graph is 3 because you have a triangle, but you don't have 4 mutually adjacent vertices. Now, the clique number feels like it should give you a lot of information about the chromatic number, because in this particular graph, it was exactly the presence of a triangle that forced us to use 3 colors. But once we had used the 3 colors to color this triangle, we had no more obstacles. We did not have to introduce a 4th color in order to continue, in order to get a successful coloring of the graph. So it feels like it should be the case that if you could identify what is the largest clique that's sitting in the graph, then that should give you some really good information about the chromatic number of the graph. You use 1 color for every vertex in that largest clique, and then hopefully you can then just use that same set of colors out around the rest of the graph. And certainly in one direction, we have the following very easy bound. The chromatic number of any graph is always at least its clique number. However, it turns out that no matter what bound you put on the chromatic number in terms of some other parameter of the graph, there are always going to be cases where that bound is really good, and there are always going to be cases where the bound is really bad. Now, we've already seen, no, we haven't actually already seen, but we're about to see an example where the clique number of the graph takes 1 value, but the chromatic number takes another larger value. And it's not a very difficult example to come up with. So in general, the clique number is not equal to the chromatic number. And here's a very simple example. You just take a cycle on 5 vertices. So what's the clique number of this guy? The clique number of the cycle on 5 vertices is 2 because it doesn't have any triangles. But what's the chromatic number? Well, we would like the chromatic number to be 2, so let's try to color it with 2 colors. I give this guy color 1, this guy color 2. Now this guy has to get color 1, this guy has to get color 2, and there's a parity problem here. We come around to meet ourselves again, and the last vertex is adjacent both to something colored 1 and something colored 2. So it has to get colored 3, and so the chromatic number of this graph is 3. But maybe the chromatic number is never more than the clique number plus 1, or 10 times the clique number, or the clique number squared. Unfortunately, not the case. So I want to tell you about the following result that gives some indication that the chromatic number is not in any way a local quantity of a graph, even though it's very much defined locally. So the claim is that for all k bigger than or equal to 2, there exists a graph such that the clique number of the graph, let me do the chromatic number first. The chromatic number of the graph is k. So you can make the chromatic number as large as you want. You can make it 1,000,000, you can make it 1,000,000,000, you can make it a Googleplex. But the graph has the smallest possible realistic clique number equal to 2. So the presence of a triangle in this graph here forced the chromatic number to be 3, but you can force the chromatic number of a graph to be 10,000 without ever inserting a triangle. This guy here gives us a hint in that direction. We're forcing the chromatic number to be 3 without introducing a triangle. And actually, the proof that we're going to give of this claim is going to involve a construction where we start off with this example, and we're going to build up from this example to an infinite family of examples, so that the kth member of the family has chromatic number exactly k, but only has clique number 2. And the construction is going to be, and now I'm going to have to, or do I have to consult my notes? So my notes are away in my backpack. So I may commit an error here, because the construction is the Michalski construction, and I may very well spell Michalski's name incorrectly, but I'll check myself and I'll send out an email if I do. So Michalski, let's do the usual I before E except after C. So that would mean that I should spell his name like this. So Michalski, a Polish-American mathematician of the 20th century, he gave the following lovely construction, a way of taking one graph and building out of it a bigger graph. And it turns out that Michalski's construction is going to have, it has lots of properties, but it's going to have 2 properties that are relevant to us. The first is that if you feed into the Michalski construction a graph that doesn't have a triangle, then what you get out the other end also doesn't have a triangle. And if you feed into the Michalski construction a graph which has chromatic number k, then what comes out has chromatic number k plus 1. So it's a way of increasing the chromatic number without increasing the clique number. And here's how it goes. You have G on vertex set V, and it's probably going to be helpful to have names for the vertices in V. I'm going to call them V1 through Vn. And here's how I'm going to produce the graph M of G, the Michalskian of G. So the vertex set is going to be V together with another set that I'm going to call W, together with one more vertex that I'm going to call Z. And V is the same V as before. W has the same size as V. It's going to be W1 up to Wn. And what are the edges of the Michalskian? Well, let me write down what they are, but it's going to be much easier then to illustrate it with a picture. So inside V, we're going to have exactly the same collection of edges as we had in G. So basically, I'm going to start with a copy of G. Inside W, I'm not going to put any edges. So W1 up to Wn are just going to be n vertices with no edges connecting them. Between V and W, here's what I'm going to do. I'm going to put an edge from Vi to Wj if and only if Vi, Vj was an edge of G. So if V1 and V2 are adjacent in J, then W2 is going to be adjacent to V1, and also W1 is going to be adjacent to V2. And what about z? Z is going to be adjacent to all of w. So that's the construction of the edges. That's maybe not entirely transparent, just writing it out like that. It's going to be much simpler if I, just in case you're wondering, I keep looking down here because I want to check that my, my microphone is still on. It's not a nervous tick. So, so what would be an example? Let's say, for example, that G was the graph consisting of a single edge, V1 joining V2. Well, what will the Michałkian of V look like? It will be, OK, I start off with a copy of G, which is V1 joined to V2. And then I have two vertices, W1 and W2. And because V1 was adjacent to V2, I'll put W1 adjacent to V2 and V1 adjacent to W2. And then I have another vertex Z, and Z will be joined to all of W. Notice, of course, that this is isomorphic to the more familiar drawing of the 5 cycle. So if I start off with a single edge, then I apply the Michałki construction, and I end up with a 5 cycle. Clique number 2, there's no triangles here. There's also no triangles here. Chromatic number here is 2, but the chromatic number here is 3. OK, what if I apply the Michałki construction to this graph that I've just obtained, the cycle? Well, what am I going to get? I am going to get, sorry, brain freeze. Let's see. What I have to do is I have to start with a copy of the cycle. And what I'm going to do is I'm going to put that on the outside of my graph. These are going to be my 5 vertices of V. And now I also have the 5 vertices of W. And of course, I'm drawing the vertices of W corresponding to the vertices of V in the obvious way. And how are the adjacencies between the V's and the W's? Well, this vertex here is adjacent to this one and this one, which means that this vertex here, this W, should be adjacent to this guy and this guy. This vertex should be adjacent to this one and this one. This vertex here should be adjacent to this one and this one. This guy should be adjacent to this one and this one. And this guy here should be adjacent to this one and this one. And just so that we're clear what the vertices of this graph are, because of course where the edges cross isn't necessarily where there are vertices. These are the 5 vertices on the inside. These are the 5 vertices on the outside. And I also have my last vertex Z, which I put in the dead center. And that's going to be adjacent to each of the 5 W's. So I get this picture here. And you can stare at this picture for a while, and you will pretty easily convince yourself that there are no triangles. So I've gone from a graph that doesn't have triangles to a larger graph that doesn't have triangles. What is less easy to convince yourself of, but yeah, you can do it in this particular instance, and then we'll have the general proof in a moment, that this graph here, we started off with a graph with chromatic number 3. This graph actually has chromatic number 4. And this is a famous graph. This is, this usually goes under the name, oh, now I'm going to have to consult my notes. I know that I've written down Groth's name. Grotzsch. So this is called the Groth graph, after the graph theorist Groth. And this graph has the property that it's the smallest triangle-free graph with chromatic number 4. So Michałki construction starts out very nicely. This is clearly the smallest triangle-free graph with chromatic number 2. Not very hard to convince yourself that this is the smallest triangle-free graph with chromatic number 3. Much less easy to convince yourself, but it has been done just by looking at all graphs on 11 vertices or fewer. There aren't that many of them for a computer. this is the smallest triangle-free graph with chromatic number 4. And so let me make the two claims about that I've already alluded to about the Michelsky construction that allow it to prove that claim that we made earlier, that you can make the chromatic number arbitrarily large while keeping the clique number as small as it could possibly be. So we're going to have two claims. I'll state them both, and then we'll work on the proofs. So claim 1 is that if G has no triangle, then neither does M of G. And claim 2 is that if the chromatic number of G is K, then the chromatic number of the Michelskian of G is K plus 1. So now we can go ahead and define a sequence of graphs GK, K going from 2 to infinity, by the following iterative procedure. G2 is the single edge, the complete graph on 2 vertices. And then for K bigger than or equal to 3, GK is the Michelskian of GK minus 1. And by claim 1 and claim 2, we have the two facts that the clique number of GK is 2, and the chromatic number of GK is exactly K. So these two claims are just what we need to prove the result that I claimed a little while ago. First of these two claims, that's nice and easy. Okay, so let's go back to the green. Okay, so proof of claim 1. I want to convince you that the Michelskian of a triangle-free graph is also triangle-free. So what do I want to do? I want to, just want to do exactly that. So here's the Michelskian of G. It's got a component, not a component, it's got a bunch of vertices labeled by V, it's got a bunch of vertices labeled W, and it's got a single vertex labeled Z. So first observation is that no triangle involves Z, because Z is adjacent only to things in W, and there are no edges between things in W. So we just can't get a triangle involving Z. The second observation, also based on the fact that there are no edges between any two things in W, no triangle includes 2 or more vertices from W, because any 2 vertices in W are non-adjacent. So of course there's going to be no triangle with 2 vertices inside W. So what is the there's one more case I wanted to do before we got to the meat. No triangle includes 3 vertices from V, because V is a copy of the original graph G, and we're assuming that that's triangle-free. So the only possibility for a triangle is going to be with 1 vertex from W and 2 vertices from V. So this is the only case in which we could possibly have a triangle. Let's say this is vertex Wi, this is vertex Vj, and this is vertex Vk. So only possible triangle involves Wi, Vj, and Vk. Okay, and notice that I, j, and k have to be distinct here. Of course, j and k are distinct because they're different vertices in V. But also, I can't be equal to j or to k, because why is there an edge from wi to vj? It's because wi and vj were, vi and vj were adjacent in v. And so I has to be different from j, and ditto I has to be different from k. And that's the key point. That's what's going to mean that this can't possibly be a triangle, because, of course, why is wi adjacent to vj? Because there is a vi here that is adjacent to vj. That's what put the edge from wi to vj in. But also, vi is adjacent to vk. That's what put the edge from wi to vk. So the only possible triangle involves these three guys. But then vi, vj, vk, a triangle contradiction. So that proves the first claim, that we preserve the property of triangle freeness. And now let's move on to the second claim. But actually, I see that I've been going for about 48 minutes, and it's probably going to take longer than 2 minutes to do the last claim. So I will pause here, and at the beginning of the next lecture, I'll pick up the proof of claim 2.